Hello, everyone. I would like to welcome you to our second lecture of the semester, where we will be discussing data sampling and probability. Because we do have some prior lectures recorded, this lecture is going to be a mix of content that we've recorded in this term in the fall and some previous content from the summer and spring terms. And so I would like to thank those who have developed some prior material, Professors Ania Dekari and Joey Gonzalez, and the summer 2020 instructor, Suraj Rampur, who is now in our GSI team, and with whom we'll be sharing some of these lectures. Today, we want to talk a little bit about the core ideas around how do we acquire data and what does it mean to sample data. Why do we need to sample in the first place? How do we construct sampling strategies when we're looking for data around a given problem to limit the biases, and what does it mean to be biased? And we will later transition into discussions around probability, which will continue on our next lecture. And we're going to do a little bit of a review of concepts that you've learned already in Data 8, but some of it will also be new material that is not completely review. Before we dig into questions around data and sampling, I want to take a moment to revisit and then illustrate a little bit a concept that we introduced already in the first lecture, which is the notion of the life cycle of data science. And this is a topic or a pattern that we're going to revisit over and over in the course of the semester. And the idea is that in real world data science work, we actually go through an iterative process where we cycle through different stages of analysis, modeling, data management, and that process is one that we keep cycling on, and it may actually start from different points. Sometimes we do have a question that we have carefully thought about and framed, and the question leads us to construct a data strategy, and we actually go out in the field, or we build an experiment, or we build a survey, or we connect to data sources that allow us to construct the samples of data that we will then use to analyze. So we start from having framed a question from which we then devise a data acquisition strategy. And then once we have these data, we perform a process of trying to first understand a little bit what's happening in the data. And this is a process that we will spend a fair amount of time into. It's called exploratory data analysis, where we actually use a combination of visualization techniques, both graphical visualization, but also looking directly at the data itself. Sometimes it's useful to just look at the numbers. And statistical techniques as well that help us get a sense of how does this data connect to the questions we were asking in the first place. And then from this, eventually we start building what are called models, where we are now trying to say something not only about what is in the data, but actually make what is called an inference about the world, and where we now make an assumption that these data represent something about the real world, and we try to build a model that tells us something not just about the properties of this particular data set we have, but also about the rest of the world. And then we build from the results of that, we communicate our results to others, we make decisions, we communicate insights, we've learned something, and this could be a report, it could be an academic paper, it could be a decision that you make in a company about a product, about a strategy, etc. But importantly, this process is iterative and doesn't always start with having a question up front that we've devised. Sometimes we actually start from data. Sometimes data exists in the world, and we actually, from the data, we dig a little bit, and then we formulate questions. And today the world is rich enough in data that it is not uncommon to actually start from data. Obviously, data that represents a context we are interested in, and where we perhaps have a set of related questions about a problem that we'd like to understand, but where the specific question that we're going to try to squeeze sort of out of the data is one that we have to iteratively construct. So it is important to appreciate that we may come into this cyclic iterative process from different points, and we're going to illustrate this with a nice simple example from a data visualization article that was posted in the New York Times a little while ago, and the slides have a link to this, which in this case started with a question: how many squirrels are there in Central Park in New York City? A journalist from the data visualization team at the New York Times basically tried to dig into this topic, it turns out that even though many ecosystems are heavily studied, Central Park, which is in the middle of New York City, was one where the squirrel population had actually not been counted. And so this journalist actually went in and joined an effort to try to count the population of squirrels in the park. Now, it turns out that in general, having good, accurate ecological counts of animal populations is an important task in ecology to understand how ecosystems change over time. And if we don't keep track of those numbers over time, it is very difficult later to make statements about, for example, what is happening as environmental conditions change to the populations. And so this particular journalist joined an effort to try to count the population of the park, and this involved actually doing data collection and getting into the field. And so this particular journalist actually went and talked to the folks who had designed the study, and she was given a task of going into the field and for 20 minutes count how many squirrels she saw. And it turns out, I would encourage you all to take a look actually at this visualization in more detail. There's a lot of interesting points being made in here about how the data was acquired, what she had to do in the field, what her observations were, the problems that she encountered following the squirrels, etc. The kinds of noises they made, the kinds of field observations that were taken in addition to counts, like drawings and diagrams and pictures. And then eventually they ended up with a count that produced a map of the squirrels in Central Park. It turns out that they had over 3,000 squirrel sightings. But very importantly, that led to now trying to produce an estimate of the actual squirrel population. If you're standing in Central Park for 20 minutes at a time, and you're simply looking around and counting squirrels, that doesn't exactly tell you how many squirrels there are in Central Park, because you don't have a way of asking all the squirrels to please line up every squirrel in Central Park and go to the left and start going in front of you one at a time so that you can count them all with a clicker, the way, for example, is done in theaters, say, when they count how many people are entering to an event. So it turns out that that decision requires how to construct that number, which is the answer to the question we wanted, how many squirrels are there in Central Park, is a step that requires building a model. And so the ecologists in this case used a formula from a paper in 1959 that actually produced this kind of information and led to generating a population estimate. But I want to connect us at Berkeley in data science a little bit closer to the literature and to the question of modeling, because the journalist in the New York Times mentions that she actually went to the library and has a picture there of the formula in the library. But it turns out that you can actually, with your Berkeley Library proxy, you can access that paper. It's a paper from 1959, but it's available as a PDF. And this is a screenshot from that article. This is a screenshot taken from the section that she took a picture of. And I want to highlight a couple of things. First of all, the journalist mentioned that she was assigned an area to walk about and search for 20 minutes. The formula that the ecologists used to produce an estimate of the population of the squirrels assumes that the observation points were visited in sequence for 15 minutes at a time instead of 20 minutes. And so we may ask, does that matter or not? Why did they use a formula that had a different assumption? Why was their data acquisition process different from the original, the one in the formula that they used? This is the actual formula that was used to try to construct an estimate of the squirrel population in a lot based on the area of the woods. In the case of the original study, it was 10 acres. In her case, she probably had the area that she was the size of the area that she was looking at, how many squirrels she saw. Okay, that's her count. The number of observation periods, but in this case they are different in terms of their length, and we should ask ourselves, does that matter or not? It is something to, whenever you use a model, you need to understand its assumptions. The formula also includes the average of all the distances from the observer to the squirrel seen. You should ask yourself, well, how does she know those distances? If you're standing in Central Park and you're looking around and you're counting squirrels, you don't exactly have a laser finder that tells you the exact distance between you and the squirrel, right? So how were these distances estimated? Is there any error? Is there any uncertainty in these? These are all questions that are important to connect the raw observations that the person acquiring the data recorded into a prediction, which is fundamentally what we call a model, right? And then finally, there's this constant 0.6. And I want to highlight here that how this constant appears in the formula. If we simply look at this formula, it looks very mathematical, but it turns out that that constant was used because it was believed that only that much of the circle around the observer could be well seen. So they're basically saying, well, we're going to guess that roughly on average you can see 60% of the field around you, and there's squirrels that you miss because they may be behind you, for example, and that on average a person can look at this much of the circle around you. So this is information that all goes into the construction of the model, from which we then construct a final answer based on the data that we got. And that is part of the data science life cycle that you need to be always aware of and critical of, because these assumptions have an impact on the conclusions that you draw. And again, I encourage you to take a look back at the complete New York Times visualization and to think about these issues, because they will be recurrent. Now, this particular illustration was a case where we actually got samples of data. There is a concept that is very important in data acquisition, which is the concept of a census, and we're going to discuss it for a minute. A census, which you may have heard about this year because it's been all over the news, that was the U.S. decennial census. It was held in April of 2020, and it is a process that is meant to count every person that lives in all 50 states, Washington, D.C., and the U.S. territories, and not just to count U.S. citizens, but anyone who happens to be living in the U.S. at the time for whatever reason. The census is mandated by the Constitution, and everyone is required to participate by law. It turns out that the information collected in the census is used for a variety of important decision-making processes, for how to allocate federal funds for a number of issues. It is used to define congressional representation districts, to allocate. So congressional districts are allocated based on the population because they're meant to represent the population proportionally. So knowing where there are people is extremely important to the political process. And not only how many there are, but actually where they are specifically, their geographic distribution, and it is a topic of, as you can imagine, heavy political debate. Now, by definition, a census is an official count of a population, where you typically record lots of details, not just how many, it's not just counting, but typically getting additional information about that population. But the point is that it is meant to be a count of the entire population. And this is important because a census is, in a sense, the gold standard of data acquisition. It is when you can count everyone, when you attempt to capture the entire data about a population. And we rarely have access to a census. We typically have to do what is called sampling, which is to get a subset of a population and to try to infer from a limited subset what happens to the entire population, because a census is in most cases impractical. For example, a decennial census is something that is only done every 10 years and takes an enormous amount of preparation and resources to conduct. So we can't be doing population censuses every single year. And in any given context, if you could imagine doing a study about, for example, Berkeley students, in many cases, it may not be practical to actually ask questions of every single student. And so we often have to select a subset of the population. And this is the process of sampling. And now we're going to talk about surveys, which are related. Rewind again. And now we are going to talk about surveys. A survey is a set of questions that are asked often in the context of a census, where we actually use a survey as a way of getting additional information beyond simply a count. And the process of conducting a survey is actually a fairly involved one. If you want to learn a lot more about the process of how we design surveys, we have a course, Stat 152 at Berkeley, which is called Sampling Surveys, where this topic is covered for an entire semester. Here we're only going to allude to a few important questions. In particular, in the context of something like a census, what kind of information is collected from people is extremely important. As we mentioned, the census is used for making many decisions, so we want to collect comprehensive information. But how we ask questions can have an important impact in the data that we get. People may respond differently based on their expectation or their assumptions about what the information will be used for, what kind of decisions will be made based on it, what impact it may have on them. And that may lead to either changes in how they respond, the truthfulness of their answers, the completeness of their answers, or even whether they choose to participate at all or not. This year, you may have heard in the news that this was a topic of quite a bit of debate because the administration, the federal government, wanted to include a question about citizenship in the census itself. And eventually, this went all the way to the Supreme Court, which stopped the inclusion of the citizenship question in the census. This was a topic of a lot of debate because the idea is that the census should be a complete count, as we said, of the whole population, regardless of whether folks are citizens or not. And there was a lot of concern that people might be afraid of participating in the census if they were not citizens because of the implications it might have on their lives. And so this is a case where how the survey is conducted and how the census is conducted may actually affect the quality of the data that we get and how it connects with a number of ethical questions. Now, it turns out that this is not a hypothetical. The agencies that conduct the census, a variety of different agencies, actually conduct other surveys over time. And we have evidence, for example, that in California, based on other data that we have that comes from different sources, from other surveys that we can complement, we have evidence that Hispanic children are going uncounted. And so this is data. This is data collected, as I said, from other surveys that we can cross-check that indicates that in these counties there are significant numbers, in particular in Los Angeles County, there are significant numbers of Latino children who are not being counted in the census. And finally, as we wrap up this section, before we move on to the next one, I want to leave you with a question, which is, and you can think a little bit about this, and there's quite a bit of interesting literature on it, which is how and why are different parts of the country investing into making the census be as complete and comprehensive as possible. For example, we have data that shows that California spent a significant amount of money trying to make the census very comprehensive, but in Texas, no funds were allocated to do this. And so the question of why different states would make different decisions on this process is one worth taking a moment to think about. So, and for the next lecture, we will, for the next segment of this lecture, we will continue with actually material recorded by our instructor, Siraj, over the summer. And we'll be mixing material and lecture recordings that are new together with some of the existing one from previous terms. Thank you.